Now that we have some basic probability under our belts, we can look at some more complicated ways of describing events. We'll have a couple different ways of describing events, and we'll see that each different way of describing events or an event sort of comes with its own way of calculating the probability of that event. So for our first one, let's look at the complement of an event. The complement of an event, which is written E bar, E with a little bar over the top, that's just the event composed of all of the outcomes not in E itself. So you can think of E bar as being just the event not E, or the event that E does not happen. So for example, if we rolled a 6-sided die, then the complement of the event odd is not odd, because all the odd outcomes, 1, 3, and 5, the complement of that is the other outcomes, that's 2, 4, and 6, and that's not odd, which is the same as even, of course. And another example, the complement of the event 2 is all of the outcomes that aren't 2's, and that's 1, 3, 4, 5, or 6. The way that we can calculate a probability using a complement is using this formula. So the probability of the complement of E is just 1 minus the probability of E itself. That kind of makes sense because the number of outcomes in E is all of the outcomes minus the outcomes not in E. So if you put this fraction, if you put the two pieces here over a common denominator, you just get the formula on the right. So the probability of a complement is 1 minus the probability of the original event. That seems like it wouldn't give you a great new way of calculating a probability, but the point here is that you always have a choice. You can always choose to calculate the probability of the event that you're looking at, or the probability of its complement. And sometimes the complement is a lot easier to find the probability of than the original. Just for an example, if you're rolling a die, the probability of not rolling a 2 is 1 minus the probability of rolling a 2. The probability of rolling a 2 is, well, there's only one outcome that's a 2, so the numerator here is just 1. And the state space for rolling a 6-sided die has 6 things in it, so the probability of rolling a 2 is 1 over 6, and 1 minus 1 over 6 is 5 over 6. And yes, that is the right probability for not rolling a 2, because not rolling a 2 means you could roll a 1, 3, 4, 5, or 6, and there are 5 outcomes that aren't 2's, so 5 over 6. So you can see this formula does produce the correct probability for the complement. Let's look at a couple examples. So what's the probability of drawing something other than a 5 from a 52-card deck? So we could write that like this. Something other than a 5, that would be the probability of not rolling a 5. But that means it's really the complement. So this is the probability of the complement of rolling a 5. All right? Well, I don't know about you, but I don't want to go count up all of the cards that aren't 5's. That seems like it would be a lot of work. So instead of finding the probability of this event not 5 directly, we can use this formula for the probability of a complement, and we can calculate 1 minus the probability of drawing a 5. This is much easier because there aren't that many 5's in the deck. There are only 4 of them, one from each suit. And so the probability of drawing a 5 is all of the 5's, and there are 4 of them, divided by the number of cards in the deck, which is 52. So this is 1 minus 4 over 52 is 1 over 13, I think. And 1 minus 1 over 13 is 12 over 13. You can see using this formula to find the probability of the complement was a lot easier than finding the probability of the complement directly. It saved us a lot of counting up a bunch of different cards. All right, let's have a look at another example. What's the probability of rolling more than a 3 on 2 6-sided dice? And since we're rolling 2 6-sided dice, there are a couple things we should worry about. One is, what is the state space? And the other is, what is the 3? This 3 here is really the sum of the outcomes on both dice. So we're rolling 2 dice, and we're going to add the results together. Okay, so now let's get a handle on the state space, or the sample space, sorry. To write down the sample space, we need to, each outcome in the sample space should completely describe the result of one result of the experiment. So, we can't just write 1 for an outcome, because we need to describe what both dice came up as when we describe this sample space. So the first number could be the outcome of the first die that we roll, but then we need to say what the outcome of the other die is. So maybe 1, 1. That means we roll a 1 on the first die and then a 1 on the second die. Another outcome would be a 1 on the first die and then a 2 on the second die, and then maybe a 1 and a 3, and a 1 and a 4, and a 1 and a 5, and now I'm running out of room, a 1 and a 6. And then we could roll a 2 on the first die, and a 1 on the second die, and then a 2 and a 2, and so on, all the way down to a 2 and a 6. And then a 3 on the first die, and so on, all the way up to a 6 and a 1, and a 6 and a 2, and a 6, all the way up to 6 and a 6. And that's a lot of possibilities. I would not want to go through all of these different possibilities and count up which of them give you a total of more than 3. There are just so many possibilities. In fact, how many possibilities are there? Well, there's 6 possibilities for the first die, 6 possibilities for the second die, so that's 36 possibilities total. And I don't want to go counting up which of them give me more than a 3 total. So instead of calculating the probability of getting more than 3, let's think about a complement. Well, getting more than 3 is the complement of getting less than or equal to 3. So we could, instead of calculating the probability of getting more than a 3, we could calculate 1 minus the probability of getting less than or equal to 3. And the nice thing about this is there aren't that many outcomes whose total is less than or equal to 3. In fact, we can count them up. There's 1, 1, 1, 2, and 2, 1. So there's only 3 of them. So 1 minus 3 over 36. That's 1 minus 3 over 36 is 1 over 12. And so that's 11 over 12. All right, you can see this switching to the complement saved ourselves a lot of work on this one. Okay, another complication that can arise is you can have an experiment that has multiple parts. So for example, for our experiment, we could roll a die and draw a whole number from 1 to 3. In this sort of situation, the state space can get a little complicated. And remember, when you write out when you're thinking about the state space, you have to a single outcome has to completely describe the total outcome of the experiment. So I keep saying state space. This should be sample space. State space is a term from physics. So just to list all of the outcomes in the sample space, let's see, we could roll a 1 on our die and then draw a 1 from the hat. And we could roll a 1 on the die and then draw a 2 from the hat, or a 1 and then 3. Then we could roll a 2 and draw a 1, roll a 2 and draw a 2, roll a 2 and draw a 3, and so on. All the way up to we could roll a 6 and draw a 1, roll a 6 and draw a 2, we could roll a 6 and draw a 3. Okay, so how many is this total? Well, our experiment has 2 pieces. There's rolling a die, and then there's drawing a whole number from 1 to 3. And these 2 pieces don't interact in any way. They're completely independent. And the number of outcomes for rolling a die is 6, and the number of outcomes for drawing a number from 1 to 3 from a hat is 3. And so the total number of outcomes is just 6 times 3, so that's 18 possible outcomes. So our state space has 18 outcomes in it. Now that we know the number of outcomes in a state space, we can use it to calculate a probability. So what's the chance of rolling a 1? So probability of rolling a 1. We just need to count up all of the possible ways to roll a 1. But there are only 3 outcomes where we're rolling a 1. It's these 3 right here. So 3 divided by the total number of outcomes, that's 18. And that's 1 over 6. That's another example, the chance of rolling a 1 and drawing a 2. So probability of rolling a 1 and drawing a 2. Well, there's only one outcome where we roll a 1 and draw a 2. That's this outcome right here. So 1 outcome divided by 18 outcomes total. And when you have an experiment that has multiple parts, often your events, well, there's a nice way to calculate the probability of events. So when events come from 2 parts of an experiment that don't have anything to do with each other, we call those events independent. So just for an example of some independent events, if you roll a die and draw a card, now those 2 parts of the experiment have nothing to do with each other. So an outcome from rolling the die and an outcome from drawing a card, like drawing an ace, these 2 are independent events. As an example of 2 events that aren't independent, imagine drawing a card from a 52 card deck and then drawing another card. The event drawing a king and then drawing a 10 are not independent, because think about that second draw. You've already taken a card from the deck, and so your chance of drawing a 10 depends on what you drew the first time. So in this example, since the second part of the experiment is influenced by the first part of the experiment, these 2 events are not independent. Now, if you do have independent events, there's a very nice way to calculate the probability of them. If you want to know the probability of one independent event A and another independent event B both happening at the same time, you can just multiply their individual probabilities. So for example, if you're rolling a die and drawing a card from a deck, the probability of rolling a 4 and drawing an ace, these are independent events because the die roll does not influence the deck and vice versa. Since these are independent events, we can just multiply the probability of drawing a 4 by the probability of drawing an ace. But the probability of rolling a 4 is 1 out of 6, and the probability of drawing an ace is 1 out of 13. So this total probability, we just multiply these together. It's 1 over 6 times 13. So that's 60 plus 18, 78. All right, let's look at a couple examples. So if you flip a coin and draw a card from a 52 card deck, what's the chance of getting heads and a heart? So this experiment has 2 parts. There's flipping a coin and drawing a card. So for the coin, there are 2 outcomes, heads and tails. And for the drawing a card from the deck, there's 52 outcomes. So we want to know what is the probability of getting a heads and getting a heart. Well, because these 2 parts of this experiment don't influence each other, these 2 events are independent. So to calculate the probability of getting a heads and a heart, we can find the probability of getting a head and just multiply by the probability of getting a heart. Okay, so when you flip a coin, the probability of getting heads is 1/2, because there's 1 head out of 2 sides. And for the probability of getting a heart, there are 13 hearts out of 52 cards. 13 over 52 is 1 over 4. So this is 1 over 8 total. All right, you can see this is much better than writing out all of the different outcomes from all of the sample space and counting up which ones have the outcome that we wanted. In this particular experiment, the sample space would have 104 things in it, and I wouldn't want to go listing them or counting them up. So if you have two independent parts of an experiment, using this trick for finding probabilities of independent outcomes, independent events, is a big time saver. Okay, here's another example. Suppose the chance of stubbing your toe in a day is 1% and your chance of your mother calling you is 3%. What's the chance that you stub your toe and your mother calls you? So that would be, so probably, I'm assuming that the chance of you stubbing your toe is independent from your mother calling you. These two things have nothing to do with each other, so they should be independent. So that means to calculate the probability of stubbing your toe and getting a call from mom should be the probability of stubbing your toe times the probability of getting a call from your mom. The probability of stubbing your toe is 0.01. We need to write this as a decimal because we're going to do some calculations with this. The probability of getting a call from your mom is 0.03. And then we can just multiply these. So 0.01 times 0.03 is 0. You can just move the decimal point over a couple times. 0.0003. So that's 0.03%. So probably you aren't going to stub your toe and get a call from your mom on the same day, apparently. Another way that is often useful to describe events is using the word or. So for example, if we're rolling a die, we can describe an event out of smaller events by using the word or in this manner. So we could say the event roll a 4 or roll a 6. So, you know, this isn't a totally new thing. We could have done this before, but we would have had to write out 4, 6. And this would be our event. We'll see that there is an advantage to being able to put events together in this way. It's just with a die, there are so few outcomes that you can always just list everything explicitly. If you're drawing cards from a deck, you could say something like the event of drawing a heart or drawing a 3. And this is maybe a better example because I wouldn't really want to list out all of the individual outcomes that go into this event. There would be a fair number of them. So for this event, it's actually easier to describe the event using the word or than it is to list out the outcomes individually. Now, if you have an event that's described using the word or, then there's a formula for the probability. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. This last piece might be a little bit of a surprise, but it makes sense if you draw a diagram of your possible outcomes. So remember, the event A is a collection of items in the sample space. So here I'm sort of diagrammatically picturing the event A. The event B is also some collection of items in your sample space. To figure out the probability of A or B, we need to know how many things are in both A and B put together. Well, that's the number of things in A, right, which is related to this first probability, plus the number of things in B, which is the second piece. But, you know, if you count up the number of things in A and then also count up the number of things in B, we've double counted everything that is in this overlap. But this overlap is the event A and B. So just adding these probabilities together double counts the probability where A and B both occur. And so to take care of that double counting, you have to sort of uncount the overlap once, and that's what this subtraction is doing. So let's look at some examples. If I have 3 pairs of pants and one of those pairs is blue, and I have 8 shirts and 4 of those shirts are blue, if I randomly choose an outfit, what's the chance I end up wearing some blue? So let's try to describe what this event is, first of all. So wearing some blue, I guess this would mean that I have blue pants or a blue shirt. So we end up using this word or. Okay, and that's a giveaway that we should probably use that formula from a second ago. So the probability of blue pants or a blue shirt, that's the probability of choosing blue pants plus the probability of choosing a blue shirt minus the probability of the overlap. So minus the probability of blue pants, I'm going to start abbreviating things, so blue pants and blue shirt. Okay, so let's think about the probability of blue pants. So I have 3 pairs of pants and only one of them are blue, so this should be 1 pair of blue pants out of 3 pairs total, plus the probability of a blue shirt. So I have 4 shirts I have 4 blue shirts and 8 shirts total. So there's a 4 over 8 or 1/2 chance of getting a blue shirt. And now I have to subtract the chance of getting blue pants and a blue shirt. Well, in this situation, choosing pants and choosing a shirt, those are independent. So this last probability, because these two things are independent, we can use our formula for the probability of independent events. It's the probability of getting blue pants times the probability of getting a blue shirt. So this is 1/3 plus 4 over 8 is 1/2 minus probability of blue pants, that was 1/3, and the probability of getting a blue shirt, that was 1/2. So 1/3 plus 1/2 minus 1/6 is, let's see, this is 2/6 plus 3/6 is 5/6 minus the 6 is 4/6, that's 2/3. So the chance of wearing something blue is 2/3. Right, one last example. What's the chance of drawing a queen or a spade from a 52 card deck? So this time, the fact that we're going to be using our OR formula is kind of given away in the statement. So let's find the probability of getting a queen or a spade. Well, according to our formula, this is the probability of getting a queen plus the probability of getting a spade minus the probability of getting a queen and a spade. Okay, so the probability of getting a queen, well, there are 4 queens out of 52 cards, plus the probability of getting a spade, there are 13 spades out of 52 cards, minus the probability of getting a queen and a spade. Well, if you get a queen and a spade in a single draw, that means you drew the queen of spades, and there's only 1 queen of spades out of the 52 total. So all of these have 52 in the denominator, so 4 plus 13 is 17, minus 1 is 16 over 52. So that's going to be, what, 8 over 26, or 4 over 13. So 4 over 13 is the probability for that one. So you can see, if you have an event that's built an event or an experiment that's built out of smaller pieces, you have some options on how to calculate the probability that let you get away from just counting up all of the individual outcomes. And this can be a great labor-saving device because the number of outcomes can be quite large.